On this question, we're given the equation y equals 3 x to the fourth plus 4x cubed. We want to start by finding the critical numbers of the function. So critical numbers are going to be where your derivative is equal to 0 or your derivative is undefined. So we're going to start to find those critical numbers by calculating the derivative of this function y equals 3x to the fourth plus 4x cubed. So I'm going to carry down the 3. It's a constant multiple. Calculate the derivative on x to the fourth. That's 4x cubed. We use the power rule there. 4 is a constant multiple, and I'll use the power rule to calculate the derivative of x cubed. That's 3x squared. We'll simplify this derivative to be 12x cubed plus 12x squared. So once we calculate the derivative, we're going to create the equation where the derivative is equal to 0 to find those critical numbers. So we have 0 equals 12x cubed plus 12x squared. I can factor out the 12 and the x squared, and we're left with x plus 1. We can set each one of these factors equal to 0. And we get x equals -1 and x equals 0 as critical numbers. We have critical numbers of x equals 0 and -1. So I also mentioned that critical numbers are when the derivative is undefined. Our original function and the derivative are both polynomial functions, and so the derivative is not going to be undefined. So we don't get any critical numbers from the derivative being undefined. So our critical numbers are -1 and 0. So now that we've found the critical numbers, we want to find the open intervals for where the function is increasing and decreasing. So what we know is that the function will be increasing when the derivative is positive, and the function will be decreasing when the derivative is negative or less than 0. So we're going to build a chart that is displaying the sign of the first derivative so that we can distinguish different intervals where the derivative is either positive or negative. So we're going to use the critical numbers that we just found in order to create this chart with the sign of the derivative. So we're going to use the critical numbers on our chart of -1 and 0. And if you'll recall, these are when the derivative is equal to 0. So these values on our chart are when the derivative is equal to 0. And when the derivative is equal to 0 is an opportunity for the derivative to change signs from positive to negative. So we use these critical numbers to divide up our number line, and we're going to test these different intervals to see whether the derivative is positive or negative. So we're going to pick test points in each one of these intervals. So I'll choose -2. In this interval, I just needed to choose any number that was less than -1. In this interval, I'll choose -0.5. I needed to pick a number in between -1 and 0. In this interval, I'll choose 1. I needed to pick a number that is greater than 0. So we're going to test these points into the derivative so that I can know the sign of the derivative. So we take our test points, our test points of -2, -0.5, and 1, and we're going to test those into the derivative. And I should probably write y primes because our equation is y prime. And so if I test this into that derivative, I'll get 12 times -2 cubed plus 12 times -2 squared. So that's 12 times -8 plus 12 times 4. And 12 times -8 plus 12 times 4 will be a negative. So in this interval, the derivative is negative, or less than 0. So let's try another one, another test point of -0.5. That's 12 times -0.5 cubed plus 12 times -0.5 squared. And 0.5 cubed, that's going to be, let's get the calculator out for that one. I think it's 0.12 something, but let's double check. 0.5 cubed is 0.125. And that's going to be plus 12 times 0.5 cubed. 0.5 cubed will be 0.25. So 12 times 0.125 is a -1.5, and 12 times 0.25 is 3. And so we get a positive on that interval. Our derivative is greater than 0, or positive in that interval. And then our final test point, 12 times 1 cubed plus 12 times 1 squared, that is 12 plus 12, which is a positive. So we have a positive for our derivative in that last interval. So what we have here is that because the derivative was negative on that interval, we have an interval where the function is decreasing. So that's going to go from -infinity to -1. And then we have two intervals where the function has a derivative that's positive, and that's increasing. So that's -infinity to, oops, not -infinity, let me correct that. So that's going to be -1 to 0, and then also 0 to infinity. So now that we've done the increasing and decreasing, we're going to apply the first derivative test and try to identify all relative extrema. We're going to write those relative extrema as an ordered pair. So we're going to use the number line that we've already built to apply the first derivative test. With the first derivative test, we're looking for changes in signs. We're looking for a change from increasing to decreasing or decreasing to increasing. So as we look at this chart, we only have one critical number in which there is a change in the sign of the derivative. So here we have a change going from decreasing to increasing, and that's going to create a relative extrema. In the other critical number of 0, you can see that the signs don't change, and so that does not create a relative extrema at that critical number. So if I want to consider what type of relative extrema I have, I am decreasing on the left and increasing on the right, and that means that at the critical number of -1, we have a minimum, a relative minimum. So we're only going to have one extrema for this question, and that extrema occurs at -1. We've already determined the type of the relative extrema, and that is a relative min. So in order to complete the ordered pair for this, I need to find the y-coordinate that goes with this relative extrema, this critical number. So I'm going to substitute that critical number of -1 into the function, the original function, 3x to the 4th plus 4x cubed. So 3 times -1 to the 4th plus 4 times -1 cubed. That's 3 minus 4 is -1. So the ordered pair -1, -1 is the relative minimum for this function. So we're going to continue working with the same function, y equals 3x to the 4th plus 4x cubed. But now we're going to be finding the critical numbers of f from the second derivative. So the critical numbers for the second derivative will be where the second derivative is equal to 0 or undefined. So we've already calculated the first derivative. Earlier it was 12x cubed plus 12x squared. And now we'll calculate the second derivative. The second derivative has 12 being a constant multiple, and we'll use the power rule on x cubed to get 3x squared. 12 is a constant multiple, and we'll use the power rule on x squared to get 2x. And if we simplify, we have the second derivative being 36x squared plus 24x. I'm looking for where the second derivative is equal to 0 or undefined. The second derivative is equal to 0 gives me 0 equals 36x squared plus 24x. And I'm going to solve this equation by factoring. We have a greatest common factor of 12x. And if I factor that out, I'll have 3x plus 2. I'll set each one of these factors equal to 0 to give x equals 0. I'll subtract 2, that's 3x equals -2, divide by 3, and x equals -2/3. I have a critical number of 0 and -2/3. The original equation, the derivative, and the second derivative are all polynomial functions, and polynomial functions have no restrictions, and so we will not find any critical numbers for where the derivative is undefined. The second derivative is undefined. So we have critical numbers of -2/3 and 0. And we're going to continue. And we need to find the intervals where the graph of the original function is concave up or concave down. And we can find the concavity from the second derivative. So when the second derivative is positive or greater than 0, the function is concave up at that point. And when the second derivative is less than 0 or negative, the original function is concave down. at that point. So we're going to build a chart and determine the sign of the second derivative for the whole domain, negative infinity to infinity. So we're going to use our critical numbers of negative 2/3 and 0, keeping in mind that these critical numbers are where the second derivative is 0. So the second derivative is 0. And these are opportunities for the sign of the second derivative to change. So we're going to test in each one of the intervals around those critical numbers. So I'll choose -1 and let's use -0.5 and 1 as our test points. So we're going to take those test points and we're going to substitute them into the second derivative. And we're doing that because we want to know the concavity, and the second derivative tells us the concavity. That's -1, -0.5, and 1. And we substitute that into the second derivative. That's 36 times -1 squared plus 24 times -1. 36 minus 24 is a positive number. So on this interval, the second derivative is positive. We be consistent. I'm going to use y. The second derivative is greater than 0. And let's choose the next test point, 36 times 0.5 squared plus 24 times, that should be a -0.5. -0.5 squared is -0.25. Half of 24 is 12, so that'll be a -12. And I apologize, -0.5 squared should be a positive 0.25. A quarter of 36 would be 9. 9 minus 12 is negative. So in this interval, the second derivative is negative. And let's do our last test point, 36 times 1 squared plus 24 times 1. That's going to be a positive. And so we have the second derivative being positive in that interval, greater than 0. So once we've built the chart, we know that when the second derivative is positive, the function is concave up, and when the second derivative is negative, the original function is concave down. So our intervals of concave up would go from negative infinity to negative 2/3, as well as from 0 to infinity. The function is concave down on the interval from negative 2/3 to 0. So in this part, we want to find all points of inflection for the function. A point of inflection is when we see a change in concavity. So you'll notice that over this critical number of negative 2/3, we have a change in concavity. That's concave up to concave down. And then we also have a change in concavity over the other critical number of 0. We have concave down to concave up. So this function will have two critical numbers. We're going to write those critical numbers as ordered pairs. So the start of the first critical number, the start of the first point of inflection will be negative 2/3. We need to find the y-coordinate, and that y-coordinate will come from the original function. And the other point of inflection will start with the critical number of 0, and we'll need to find the y-coordinate from the original function. So we're going to take those critical numbers of negative 2/3 and 0, and we're going to substitute them into the original equation. The second one is easier, so let's do that. 3 times 0 to the 4th plus 4 times 0 cubed gives us 0. So we have that ordered pair 0, 0. And then the next one, we've got 3 times negative 2/3 to the 4th plus 4 times negative 2/3 cubed. So that's 3 times 16 over 81 plus 4 times negative 8 over 27. And let's see, 3 times 16 will give 48 over 81. Oh, actually, we can reduce that. Let's reduce that. 3 goes into 81 27 times, so we can write that as 16 over 27, and then 4 times 8, that will be 32 over 27, and we get negative 16 over 27. So the other point of inflection has a y-coordinate of negative 16 over 27. So we're going to continue with another couple parts on this function. We want to find both the x and y intercepts, and then we want to use the information that we have on the previous parts to draw a sketch of the graph. And so that's why you see on the left here where I've taken a summary of what we've done before. We built this chart related to the first derivative. The outcome of that was increasing and decreasing, the knowledge of the increasing and decreasing, and also the relative minimum. And then we built a chart for the second derivative, which tells us about the concavity. And then we also got some points of inflection from that chart as well. So we'll use this in just a moment to create a sketch of this equation, y equals 3x to the 4th plus 4x cubed. So before we do that, let's find the x and y intercepts. So to find a y-intercept, we're going to let x equal 0. So we have that equation y equals 3 times x to the 4th, so we have 0 to the 4th, plus 4x cubed, so that's 0 cubed, and that gives us a y-intercept of 0, 0. We also want to find the x-intercept. We're going to find the x-intercept by letting y equal 0. So that gives us the equation 0 equals 3x to the 4th plus 4x cubed. We can factor out the greatest common factor of x cubed, and that's going to leave us with 3x plus 4. We set each of these factors equal to 0. We're going to get x equals 0 and x equals a negative 4/3. So that gives us x-intercepts of 0, 0 and negative 4/3, 0. And as I'm reading this, it doesn't state to list them as ordered pairs, so we're going to list them as negative 4/3 and 0. And we have a y-intercept at 0. So now we're going to draw a sketch of the graph. And I'm going to start by putting down the intercepts, the extrema, and the points of inflection. If this were a rational function, at this point you'd also put down any vertical and horizontal asymptotes. So we have our x and y intercept of 0, 0, -4/3. Maybe I can zoom this graph in just a little bit so it's not so small. Okay, maybe not. Okay, -4/3 is 1 1/3. Then we have a relative minimum at -1, -1. Points of inflection at 0, 0. And a point of inflection at -2/3 and -16/27. I went ahead and I wrote the decimal values for those so that we would know where to plot this point. -0.67, and this should be a -0.59. So that would be about right here. So what we want to do from here is use the information from our first derivative and second derivative chart to understand how to draw the curve between these points. And we're really paying attention to how we draw the curve between the relative extrema and the points of inflection. So there are 4 different types of ways that we're going to draw the curve. And we can very easily see those different ways to draw the curve if we take a look at an up-facing parabola and a down-facing parabola. So up-facing and down-facing. So the up-facing parabola represents concave up, and it shows us the 2 different ways to draw concave up. So right here at the vertex, the left of the vertex shows us decreasing, and the right of the vertex shows us increasing. And for a down-facing parabola, that shows us the 2 different types of ways to draw concave down, and that's separated by the vertex. On the left, that shows increasing, and on the right, it shows decreasing. So these are the 4 different ways to draw the curve. So this section here is decreasing and concave up. This section is increasing and concave up. This section is increasing and concave down. And this section is decreasing and concave down. So if we take a look at our 2 charts with the first derivative and second derivative, so let me bring those 2 together so we can see them at the same time. We're going to understand how to draw the curve on each one of the intervals. So the smallest value on these charts would be the the smallest value would be the -1. So looking at the chart here, I'm focusing on this interval to the left of -1. And maybe I should use a different color. How about this color here? So on this interval here, and -1 would be right here on this chart. And what I see is that the function is decreasing. I'm looking at the first derivative chart and it is decreasing, and the second derivative chart is concave up. So at -1, this is the value of x equals -1. I want to draw the curve that is to the left of that point, decreasing and concave up. So I'll connect it with that x-intercept. And I'm drawing the curve so that it is decreasing and concave up. So then the next section I'm going to focus on. Let me use a different color. So the next section I'll focus on is with this -2/3 here. That's the next smallest number. And I'm still in that same interval over here where the function is concave up, but negative 2/3 is going to fall in this interval right here where we are increasing. So connecting an x of -1 with an x of negative 2/3, I'm going to draw that as concave up and increasing. And then I'm going to look at the next section. So the next number over would be 0. So in this section here, my second derivative is negative, so concave down. And this section here, my first derivative is positive, so it's increasing. So when I connect these 2 points, I want to draw concave down and increasing. And then in the last interval, let's get a new color here. In the last interval, the function should be increasing and concave up. So I'll draw increasing and concave up in that last interval. So that gives me a sketch of this function without looking at the graph using calculus to determine it. On this question, a farmer plans to fence a rectangular pasture adjacent to a river. No fencing is required along the side adjacent to the river. The farmer has 2,400 feet of fencing. What dimensions will produce the largest area? So in this question, we have a river, and this farmer plans to create a pasture with some fencing, and the fencing is going to go up along 3 sides. As it's stated in the problem, we don't need to put any fencing up along the river. We know that we have 2,400 feet of fencing, and that's going to go up on those 3 sides. We want to produce the largest area for this pasture, and because we're trying to find the largest area, we know that this is an optimization problem. Optimizing is finding the optimal number, and that means we have an optimization problem. So we need to create an equation that represents area so that we can use calculus to optimize or find the largest area. So we know that from our figure, our pasture is rectangular, and we can find the area of that pasture by doing length times width. So this is going to be our primary equation, the equation that we're going to use the calculus on. But in our calculation, in the calculus, we need to have only one variable in our area equation. And so we need to use some of the other information in the problem, like the 2,400 feet of fencing, to reduce the number of variables in the equation. So I'm going to label these sides as x, and then I'm going to label this longer side as 2,400 minus 2x. And this gives me a way of having the sides labeled with only one variable. So I'm using x and x on these 2 sides. The remaining amount, the remaining fencing is going to go on this longer side. So I'll take the total amount of fencing minus the 2 sides. So that's going to allow me to create this area equation to be 2,400 times x. Excuse me, I didn't finish my thought there. 2,400 minus 2x, that's the length, times the width of x. So this gives me the equation 2,400x minus 2x squared. And I like to write that in descending order. So we have negative 2x squared plus 2,400x. So now we have an equation with only one variable, and we're ready to use our calculus techniques to optimize the area, find the largest area. So to optimize it, we're going to first look for critical numbers. So we need the derivative. The derivative is negative 4x plus 2,400. We want to know where the derivative is equal to 0. So we have negative 4x plus 2,400 equal to 0. Negative 4x equals negative 2,400. Divide by negative 4. And we have x equals 600. So this is our critical number. We think that this is going to be the optimal value, but we still need to confirm that with calculus. So I'm going to calculate the second derivative. And the second derivative will be negative 4. And because my second derivative is negative, that tells me that the function is concave down for the whole function, but in particular at this critical number that we found here. So that's significant because we have a function that is concave down, and concave down is something that looks like this. And we also have this critical number, which is where the first derivative is equal to 0. So that tells me that we're dealing with a point that has a horizontal tangent line. So that combination of being concave down and having a horizontal tangent line tells me that I'm dealing with a maximum value, which is what we were looking for in this problem. We're looking for the largest area. So we're going to be able to create a pasture with the largest area when x is equal to 600 feet. So that is the side that's going perpendicular to the river. And then we can find the side that is parallel to the river. That's 2,400 minus 2 times 600. 2,400 minus 1,200 is 1,200. 1,200 feet. So the dimensions of the pasture will be 1,200 feet going parallel to the river and 600 feet going perpendicular to the river. On this question, we are given the first derivative, and we're going to calculate the second derivative and use some algebra to clean it up. So this derivative is in fraction form, so we're going to use the quotient rule to calculate the derivative. And so the quotient rule, we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. All over the denominator squared. So that gives x squared minus 1 squared times the derivative of negative 3x squared, that should be an x squared, plus 1, so the derivative of that, minus negative 3 times x squared plus 1 times the derivative of x squared minus 1 squared over the denominator x squared minus 1 squared squared. So we're going to calculate these two derivatives. And that gives x squared minus 1 squared times that -3 is a constant multiple, so I'll carry that down and calculate the derivative inside the parentheses. So the derivative of x squared is 2x, and the derivative of 1 is 0. And then I'll calculate the derivative of x squared minus 1 squared, and I need to use the chain rule. So I'll bring that power down, leave the inside alone, take 1 away from the power, and chain by multiplying by the derivative of the inside. So that gives 2 times x squared minus 1 over 2x. In the denominator, I can simplify using the power rule for exponents to give x squared minus 1 to the 4th. I multiplied those powers together. So what I'm looking for now is some algebra simplification. And what I notice is that I have x squared minus 1 in the denominator, x squared minus 1 in both terms in the numerator. So that means that I can cancel out a factor of x squared minus 1. So typically what I would do at this step would be to factor out that common factor and cancel. But I'll show a slightly different approach in that I could cancel at this point. So because I have that common factor in the denominator, I can cancel that factor, cancel one of the factors from here, and cancel one of the factors from here. This is going to make it a little bit easier to deal with. We have x squared minus 1 times negative 6x. A minus and a negative will make that a plus. 3 times x squared plus 1 times 4x. All over x squared minus 1 cubed. So what I'll do at this point is use the distributive property and then combine like terms. That would give negative 6x cubed plus 6x. And then I would have 12x cubed plus 12x. And that is over x squared minus 1 cubed. You can combine like terms to get 6x cubed plus 18x over x squared minus 1 cubed. And I can factor out a common 6x. And I'll be left with x squared plus 3 over x squared minus 1 cubed. For this question, we want to solve the problem using calculus techniques. We're going to show all of our work. And in this question, we want to find two numbers whose difference is 100 and whose product is minimum. So we have two numbers, and I'm going to let the first number be x and the second number be y. And we want to find two numbers whose difference is 100. That gives us one equation. If their difference is 100, I can write x minus y equals 100. And we want to find these two numbers whose product is minimum. So their product, x times y, is minimum. And the fact that we are trying to find the minimum value means that this is an optimization problem. And we've already created an equation that represents the product that we're trying to minimize. So we have the equation here, x times y. But the problem is that we're using single variable calculus, and so we need for our equation to have only one variable in it. So we're going to use this other information, the fact that their difference is 100, to reduce the number of variables in our equation that we want to optimize. So if I rewrite that equation, I can add y to both sides, and it gives the equation x equals 100 plus y. And then I can make a substitution in for x into that product, and that gives me the equation 100 plus y times y. And I'll use the distributive property to get 100y plus y squared. And I can also write this in descending order. That's my preference. So that's y squared plus 100y. So now I have the product of these two numbers written as an equation with only one variable. So I'm ready to do my calculus techniques on this equation. So I need to find the critical numbers. And the critical numbers are when the derivative is equal to 0 or undefined. So I need to calculate the derivative. The derivative will be 2y plus 100. And I'll set that derivative equal to 0 to find the critical numbers. I'm going to subtract 100, and that gives negative 100 equals 2y. Divide by 2, and y is negative 50. So this is my critical number, which I believe to be when the product is minimum, but I need to verify this with calculus. So to verify it with calculus, I'm going to calculate the second derivative. So the second derivative will be 2, and that second derivative is positive or greater than 0. And when the second derivative is positive, that tells me that the function is concave up. So if the function is concave up, then the graph will look something like this. And that information combined with having a critical number is when the derivative is equal to 0. That means that we have a horizontal tangent line. Horizontal tangent line combined with being concave down means we have a minimum. So that's verifying that that critical number that we came up with, negative 50, is a minimum. So this process that we're going through here is called the second derivative test. So you first find the critical number from the first derivative, and then you use the second derivative as a test to tell the concavity, and that verifies whether you have a minimum or a maximum, a relative minimum or maximum. So we've just found that y is equal to negative 50, and we can find x. X will be 100 plus negative 50, which is 50. So x equals 50 and y equals negative 50 are the two numbers whose difference is 100. If we do 50 minus negative 50, their difference is 100. And the product of those two numbers, 50 times negative 50, will be the minimum value. And that's a negative 2500 is that minimum product. Thank you for checking out my videos. Have a great day.